Hello and welcome to my YouTube channel ChemWis. In this video, we are going to learn isomerism in organic compounds. We will start with the definition and types of isomerism. Before going to isomerism, we should first know what are isomers. You might have seen that there are more than one different compounds having same molecular formula. These are called isomers. So, we can define isomers as compounds with the same molecular formula but different structures and or different properties. Come to the isomerism. The isomerism is defined as the phenomenon of existence of more than one compounds having the same molecular formula but different structures and or different properties. Isomerism is of two main types: structural isomerism, also called constitutional isomerism, and stereoisomerism. Structural isomerism is further divided into 6 different subtypes: chain isomerism, position isomerism, ring chain isomerism, functional group isomerism, Metamerism, and Tautomerism. Stereoisomerism is divided into 2 subtypes: geometrical isomerism and optical isomerism. Now we will go into details. First, we will learn structural isomerism. Structural isomers are defined as compounds having the same molecular formula but different connectivity between atoms or groups. In this isomerism, we are first going to discuss chain isomerism. Compounds having same molecular formula but different carbon skeleton are called chain isomers, and the phenomenon is called chain isomerism. For example, molecular formula C5H12 is the common molecular formula for 3 different compounds: normal pentane, isopentane, and neopentane. We can see here that they have different carbon skeletons but same molecular formula. So they are the example of chain isomers, and this phenomenon is called chain isomerism. Let's have the example of molecular formula C6H14. This is the common molecular formula for 5 different structures: hexane, 2-methylpentane, 3-methylpentane, 2,2-dimethylbutane, and 2,3-dimethylbutane. All have different carbon skeleton but same molecular formula, so they are chain isomers. Position isomerism. Compounds having the same molecular formula and same carbon skeleton but different position of substituent atoms or groups are called position isomers, and this phenomenon is known as position isomerism. For example, C3H8O is the common molecular formula of propane 1-ol and propane 2-ol. Here we can see that in both the compounds, 3 carbon chain is the skeleton and only position of OH is different. So they are position isomers. Second example, C5H8. This is the common molecular formula of 2 alkynes, pent 1-ine and pent 2-ine. Here in this case, both have 5 carbon chain skeleton with difference in only the position of triple bond. So these are position isomers. Example 3. Cresol has molecular formula C7H8O. There are three isomers of cresol: orthocresol, metacresol, and paracresol. Here, the skeleton is benzene and the relative position of methyl and OH is different. So, these are also the examples of position isomers. Ring chain isomerism. Compounds having the same molecular formula but different structures as cyclic and open chain are called ring chain isomers, and the phenomenon is called ring chain isomerism. For example, propene and cyclopropane have the same molecular formula C3H6, but one has open chain structure while other cyclic. So these are the examples of ring chain isomers. Functional group isomerism. Compounds having the same molecular formula but different functional groups are called functional group isomers, and this phenomenon is termed as functional group isomerism. This isomerism is shown between different class of compounds. First is between alcohol and ether. For example, ethanol and dimethyl ether. Second is between aldehyde and ketone. For example, propanaldehyde and acetone. Between unsaturated alcohol, aldehyde and ketone. For example, allyl alcohol, propanaldehyde and acetone. Between carboxylic acid and ester, for example, propionic acid and methyl acetate. Between alkyne and alkadiene, for example, 2-butene and 1,3-butadiene. Nitroalkane and alkyl nitrite, for example, nitromethane and methyl nitrite. Cyanide and isocyanide, for example, methyl cyanide and methyl isocyanide. The last one is primary, secondary and tertiary amine. For example, propylamine, ethyl methylamine and trimethylamine. Metamerism. Compounds having the same molecular formula but different alkyl groups on two sides of functional groups are known as metamers, and the phenomenon is known as metamerism. For example, diethyl ether and methyl propyl ether. Here we can see that both have the same molecular formula. In one, left and right alkyl groups are ethyl, while in other, on one side it is methyl and on the other side it is propyl. Similarly, diethylamine and methylpropylamine, 3-pentanone and 2-pentanone, methyl propanoate and ethyl ethanoate are also the examples of pairs showing metamerism. Tautomerism. Isomers which are interconvertible by just change in the position of hydrogen atom and pi bond are called tautomers, and the phenomenon is called tautomerism. Let's have a hypothetical molecule H, X, Y double bond Z. Shifting a proton from X to Z accompanied by delocalization of pi bond like this produces another species X double bond Y single bond Z single bond H. These two species are in equilibrium, which are known as tautomers. The equilibrium arrow shown between the two tautomers are of the same length, which is used when both the tautomers have the same stability. This is not a real case scenario. Generally, one tautomer is more stable than other. In that case, the arrow in the direction of more stable tautomer is longer than the arrow in the direction of less stable one. Thus, if the left side tautomer is more stable than right side tautomer, then the arrow in the left side direction will have longer length than the arrow in the right side direction. If the right side tautomer is more stable than the left, then the equilibrium arrow will be like this, where the arrow in the right side direction is longer than the arrow in the left side direction. Now let's go through examples. The first is keto-enol tautomerism. In this, the first example we are going to take is acetone. This is the keto form of acetone. It has enolizable alpha hydrogen. The relocation of the alpha hydrogen like this will give enol form. Since keto form is more stable than enol, so the equilibrium arrow will be like this. Second example is acetylacetone, the keto form of which can be drawn like this. These are two more acidic hydrogens. Relocation of one of them like this gives enol form, which is stabilized by intramolecular hydrogen bond. This intramolecular hydrogen bond makes enol form more stable than keto. So the equilibrium arrow will be like this. Third example is phenol, the keto form of which can be drawn like this. Enolization like this will give enol form. Here we can see that the keto form is non-aromatic while enol is aromatic. This makes enol form very stable, and because of that it mainly exists in enol form, and therefore the equilibrium arrow can be drawn like this. Second example of tautomerism is amide iminol, also called amide imidic acid tautomerism. Here I am taking the example of N-methyl acetamide. This is amide form. Relocation of proton from nitrogen to oxygen and change in the position of pi bond like this gives iminol form. Amide form is more stable than iminol, so the reversible arrow will be like this. Third example is lactam-lactim tautomerism. We know that lactams are cyclic amide. This is a general structure of a lactam. Relocation of hydrogen will give lactim. Since lactam is more stable than lactim, so the equilibrium arrow will be like this. Imine-enamine tautomerism. Imine is a compound formed by the reaction between a primary amine and an aldehyde or ketone. It has a double bond between nitrogen and carbon. Relocalization of alpha hydrogen from carbon to nitrogen gives tautomer enamine. In general, imine is more stable than enamine. Nitroso-oxime tautomerism. A nitroso compound with at least one alpha hydrogen can undergo delocalization of alpha proton to oxygen to produce oxime. Here, oxime is more stable than nitroso. nitronic acid tautomerism. Nitroalkane with at least one alpha hydrogen undergoes proton shift to produce nitronic acid tautomer. Here, nitro-tautomer is more stable than nitronic acid. Annular tautomerism. In this type of tautomerism, the movement of labile proton is restricted to the ring atoms. For example, 3-methylpyrazole and 5-methylpyrazole. These are annular tautomers. Another example is purine, which has 4 tautomers, 9H, 7H, 1H and 3H. Out of these 4, 9H and 7H are the predominant tautomers. Ring chain tautomerism. In this tautomerism, delocalization of proton is accompanied by conversion of acyclic isomer to cyclic one and vice versa. For example, this is open chain form of D-glucose, which is less than 0.02% in solution. It undergoes cyclization and proton shift like this to produce 36% alpha D-glucopyranose and 64% beta D-glucopyranose. These interconversion between open chain form and alpha D-glucopyranose and open chain form and beta D-glucopyranose are the examples of ring chain tautomerism. The last tautomerism which we are going to discuss is valence tautomerism. By definition, it is different from what we have discussed so far about tautomerism. We have learned so far that in tautomerism there is movement of proton from one atom to another. But in valence tautomerism, single and double bonds are continuously formed and broken in the compound without any migration of atoms or groups. For example, tautomerism between benzene oxide and oxapine. Benzene oxide undergoes electrocyclic ring opening like this to produce oxapine. Oxapine undergoes electrocyclic ring closing to produce benzene oxide. Thus, these two compounds exist in equilibrium and act as an example of valence tautomerism. Second example is homotropylidine. It undergoes co-prearrangement like this to produce equivalent structure. If there is substitution, then the two structures will be different compounds. For example, if the 2-methylene hydrogen of 3-membered ring in the left side compound are replaced by deuterium, then the right side compound will have deuterated methylene group in the 7-membered ring. Thus, we can see that these two tautomers are different compounds. The third and more interesting example of such type is bulvalene. This is the structure of bulvalene. For better understanding, label all the carbon atoms as 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Here we can see that carbon 4, 5 and 10 are the part of cyclopropane ring. If it undergoes co-prearrangement like this, it will give this equivalent structure in which carbon 1, 2 and 7 are the part of cyclopropane ring. But this molecule could have also undergone such rearrangement to produce cyclopropyl ring at 178 or 128, etc. Any of these could then undergo several co-prearrangements. So the number of valence tautomer in this case will be factorial 10 upon 3. That will be 1,209,600. Proton NMR of bulvalin at 10 degrees centigrade shows only one signal at 4.22 ppm, suggesting a fractional nature of the molecule. Now we will discuss stereoisomerism. Molecules having the same molecular formula and same connectivity between atoms or groups, but different arrangement of atoms or groups in three-dimensional space are called stereoisomers, and the phenomenon is known as stereoisomerism. We know that stereoisomerism is of two types, geometrical and optical. We will take one by one. We will first take geometrical isomerism. Molecules having the same molecular formula and the same connectivity between atoms or groups, but different arrangement of atoms or groups in three-dimensional space because of restricted rotation due to double bond or ring, are called geometrical isomers, and the phenomenon is known as geometrical isomerism. Let's take the first case where existence of geometrical isomerism is due to restricted rotation about the double bond. Rotation about a double bond, be it CC double bond, CN double bond, or NN double bond, is restricted because of sidewise overlap of two p orbitals. I will first take you through the examples of geometrical isomerism because of restricted rotation due to CC double bond. This is the general structure of an alkene. For CC double bond to be involved in geometrical isomerism, the substitution pattern should fulfill the following criteria. Here, G1 should be different from G2 and G3 should be different from G4. For example, 2-butene. There are two possible spatial arrangement of H and methyl group. In one, the two methyl groups are on one side and 2H on other side of the double bond. In other, methyl is opposite to methyl and H is opposite to H. The isomer in which similar substituents are on the same side of alkene is called cis isomer, while the isomer in which similar substituents are on the opposite side of the alkene is called trans isomer. Please note that the cis-trans nomenclature is applicable only when the two alkenic carbons have at least one common substituent. There is one more nomenclature which is universal for all alkene called EZ nomenclature. To determine EZ nomenclature, the groups on each carbon are labeled as 1 and 2, where 1 is of higher priority and 2 lower. The isomer with the same priority groups on the same side of the double bond is called Z isomer, while that having same priority group on the opposite side of the alkene is called E isomer. For more details about EZ isomerism, I have made a separate videos. You can find the link for them in the description box of this video or by clicking on I button. Similarly, 1,2-dichloroethene has two geometrical isomers, one with 2-chloro on one side and 2H on the other side of the double bond called cis form or Z, and other with Similar groups on opposite side of the double bond called transform or E. Cycloalkenes with 8 carbon ring or greater have stable geometrical isomers. For example, cyclooctane has 2 geometrical isomers, cis-cyclooctane and trans-cyclooctane. Examples of geometrical isomers due to restricted rotation about the CN double bond. These are imines and oximes. The general structure of an imine can be drawn like this. On nitrogen, there is a lone pair of electrons. For an imine to show geometrical isomerism, G1 and G2 should be different. For example, imine formed by the reaction between benzaldehyde and aniline has two geometrical isomers, one with two phenyl groups on the same side of CN double bond and other with the two phenyl groups on the opposite sides of the double bond. To find the configuration, phenyl group attached to carbon is given number 1 and H number 2. Phenyl attached to nitrogen is number 1 and the lone pair number 2. Similarly, in the other isomer, the groups will be labeled as 1, 2 and 1, 2. The isomer with the same priority group on the same side of the CN double bond is Z isomer, while that with the same priority group on the opposite side of the double bond is E isomer. An oxime can be represented like as. Here also there is a lone pair on the nitrogen. For an oxime to show geometrical isomerism, G1 and G2 should be different. Oxime formed by the reaction between benzaldehyde and hydroxylamine has two geometrical isomers, one with phenyl and OH on the same side of CN double bond and other with the phenyl and OH on the opposite sides of the double bond. For deciding the absolute configuration, let's do labeling based on CIP rules. Phenyl is labeled number 1 and hydrogen number 2. OH is number 1 and the lone pair number 2. Similarly, in other isomer, the numbering will be 1, 2 and 1, 2 like this. The isomer with the phenyl and OH on the same side of the double bond is Z isomer, while that with phenyl and OH on the opposite sides is E isomer. Geometrical isomerism due to restricted rotation about NN double bond. The example is azobenzene. In one isomer, the two phenyl groups are on the same side of NN double bond called Z isomer, while in other, the two phenyl groups are on the opposite sides of the double bond called E isomer. Existence of geometrical isomerism because of restricted rotation about the single bond due to a ring. A ring has two faces, up and down. If a ring has at least one substituent on two different ring atoms, then it will show geometrical isomerism. For example, 1,2-dimethyl cyclopropane. It has two geometrical isomers, cis and trans, depending upon whether the two methyl substituents are on the same side or opposite side of the ring. 1,3-dimethyl cyclobutane. It will also have cis and trans isomers. t-butyl 4-methyl cyclohexane. It will also have cis and trans isomer. Now come to the optical isomerism. In this, we will discuss the following points: plane polarized light, optically active compounds, optical isomerism, criteria for a molecule to be optically active, chiral center, enantiomers, diastereomers, and Meso compounds. Let's take one by one. First is plane polarized light. Suppose we have a source of light. The light is propagating from left to right. Light is an electromagnetic wave. An ordinary light from any source, be it natural or artificial, oscillates in an infinite number of planes at right angle to the direction of light. The oscillations in two different planes perpendicular to the direction of light can be shown like as. Here we have shown only two for the sake of simplicity, but in reality these are infinite in number. If we look from this side, then the oscillation of light wave will be simpler and can be shown like as. Here, the double-headed arrows of different colors are the planes of oscillation. This ordinary light, which has oscillations in infinite number of planes perpendicular to the direction of propagation of light, is called unpolarized light. When an unpolarized light is allowed to pass through certain devices called polarizer, the transmitted light has oscillation only in one plane. Rest of the oscillating vectors are not allowed to pass through the polarizer. The light which has oscillation only in one plane perpendicular to the direction of propagation of light is called plane polarized light. Optically active compounds. When a plane polarized light is passed through a solution of certain compound, the plane polarized light is rotated towards the right or left. The compounds which rotate the plane of polarized light are called optically active compounds. The compounds which rotate the plane of plane polarized light towards the right are called dextrorotatory, and those which rotates the plane of plane polarized light towards the left are called levorotatory. Dextrorotatory is indicated by plus sign or a small d, while levorotatory by a minus sign or small l. Optical isomerism. Compounds having the same molecular formula and the same connectivity between atoms and groups but different behavior towards the plane polarized light are called optical isomers, and the phenomenon is called optical isomerism. Criteria for a molecule to be optically active. For a molecule to be optically active, it should be chiral, that is, it should be non-superimposable on its mirror image. For example, lactic acid. One of the isomers can be drawn like this. If we put a mirror, this will be the mirror image of this isomer. Non-superimposable on its mirror image means if we put mirror image of a molecule over it, it doesn't completely cover it. In this case, if we put the mirror image over the original molecule, we can see that these are non-superimposable. Therefore, the lactic acid is a chiral molecule. The molecule shown on the left side of the mirror has S configuration, so it is called S-lactic acid. It rotates the plane of plane polarized light towards the right, so it is called plus lactic acid or small d lactic acid. It is also called capital L lactic acid. The isomer shown on the right side of the mirror has R configuration, so it is called R lactic acid. It rotates the plane of plane polarized light towards the left, so it is called minus lactic acid or small L lactic acid. It is also called capital D lactic acid. For a molecule to be optically active, it may or may not have a chiral center. For example, this biphenyl doesn't have any chiral center, but it is optically active due to the presence of chiral axis. The third and last point is that an optically active molecule doesn't have any plane of symmetry. For example, L-tartaric acid and meso-tartaric acid both have two chiral centers, but L-tartaric acid is optically active because it has chiral centers and doesn't have any plane of symmetry, while mesotartaric acid is optically inactive as it has plane of symmetry that makes it achiral. Chiral center: boron, carbon, nitrogen, silicon, phosphorus, sulfur, etc. act as chiral centers if they have certain substitution pattern. Boron, carbon and silicon are said to be chiral centers if they have four different atoms or groups attached to them. The general structure can be drawn like this, where X is boron, carbon or silicon, and A, B, C and E are different atoms or groups. These are the examples of molecules having boron, carbon and silicon as chiral centers. Nitrogen, phosphorus and sulfur are said to be chiral if they have four different atoms or groups attached to them. Quaternary ammonium salts with four different substituents are nitrogen, phosphine oxide with three different substituents, and sulfoxamine with two different substituents on sulfur are the example of this type. Nitrogen, phosphorus and sulfur are said to be chiral even if they have only three different atoms or groups attached to them. Here, lone pair is considered to be the fourth substituent. Amines with three different atoms or groups attached to nitrogen, phosphine with three different groups attached to phosphorus, and sulfoxide having two different groups attached to sulfur are the example of this type. Enantiomers. Enantiomers are defined as optical isomers which are mirror images of each other. In terms of absolute configuration, the two enantiomers have opposite configuration on each and every chiral center. For example, L-lactic acid and D-lactic acid. They have the same molecular formula, same connectivity of atoms and groups, but rotate the plane of plane polarized light equal in magnitude but opposite in direction. So they are optical isomers. We can see here that they are mirror images of each other. So they are enantiomers. There is only one chiral center. L-lactic acid has S configuration while D-lactic acid R. Thus, we can see that the two enantiomers have opposite absolute configurations. I am not going to discuss how to find absolute configuration in this lecture as I have made a separate video for that. I have shared the link for the same in the description box of this video, or you can also find by clicking on I button. You can use this method to find the relation between two optical isomers when they are drawn differently. Next example of enantiomers is L-tartaric acid and D-tartaric acid with two chiral centers. L-tartaric acid rotates the plane of plane polarized light towards the right, so it is also called plus tartaric acid, while D-tartaric acid rotates the plane of plane polarized light towards the left, so it is also called minus tartaric acid. We can see here that these are mirror images of each other, so enantiomers. We can also find this relation by determining absolute configuration. L has R configuration while D SS. Since they are optical isomers with opposite absolute configuration on each chiral center, so they are enantiomers. Let's have another example with three chiral centers and two molecules are drawn in a different projection formula. Here, one is in flying wedge projection formula, while other in Fisher. Here, there are two ways to find the relation between these two. The first is to draw both in the same projection formula and compare the structures. And in other, assign the configuration on each chiral center and compare. Let's first analyze by drawing them in the same projection formula. Let us convert molecule drawn in perspective formula to Fisher. Then it will become like this. Now we can see that these two are mirror images of each other. So these are enantiomers. In the second method, we will assign the configuration on each chiral center. The configuration in the left side compound are 2R, 3S and 4R, while in the right side compound it is 2S, 3R, 4S. Here we can see that these two have opposite configurations on each chiral center, so they are enantiomers. Let's have two cyclic structures. They are drawn in the same fashion. It is clearly visible that they have opposite configurations on each chiral center, so they are enantiomers. In other way, if we rotate the right side structure about this axis through 180 degrees, it will be this structure. Now we can see that these two are mirror images of each other and thus enantiomers. If we talk about absolute configuration, left side structure has RR while right one has SS. since they have opposite configuration on each chiral center, so they are enantiomers. Diastereomers. Diastereomers are defined as stereoisomers including both the geometrical and optical, which are not mirror images of each other. In optical isomerism, the two diastereomers have the same absolute configuration, at least at one chiral center, and opposite configuration at rest of the chiral centers. For example, cis and trans are E and C isomers. In this, we will take the example of cis-2-butene and trans-2-butene. In terms of E and Z nomenclature, cis-2-butene is Z while trans is E. One thing which is to be noted here is that there is no correlation between cis-trans and E and Z. This means that cis can be E or Z and so as the trans. Here we can see that these two are stereoisomers and not the mirror images of each other, so these are diastereomers. Example of diastereomers in optical isomers with more than one chiral centers. First example of this type is pair of L-tartaric acid and mesotartaric acid. Here we can see that these are optical isomers but not the mirror images of each other. So these are diastereomers. We can also find this relation by assigning and comparing the absolute configuration on each chiral center. L-tartaric acid has 2R, 3R configuration, while mesotartaric acid has 2R, 3S. Here we can see that both have the same configuration at C2 but opposite on C3. So these are diastereomers. Similarly, D-tartaric acid and mesotartaric acid are also a pair of diastereomers. Another example is pair of D-glucose and D-aldose. It is clearly visible that they are optical isomers but not the mirror images of each other. We can also draw the conclusion by comparing the absolute configurations. Here we can see that they have the same configuration at C4 and C5 and opposite configuration at C2 and C3. So they are diastereomers. Minus menthol and isomenthol. These are also optical isomers but not the mirror images of each other. So these are diastereomers. If we look at the configurations, both have the same configuration at C1 and C2 and opposite configuration at C5. So these are diastereomers. Now let's have one more pair of optical isomers to find relation. Here one molecule is drawn in Newman projection while other in Fischer. So first convert Newman to Fischer and then compare. The Fischer projection of the molecule drawn in Newman will be like this. Here I am not going to discuss how to convert Newman to Fischer, as I have uploaded a separate video on this topic. The link for the same can be found in the description box of this video. Now we can see that these are not mirror images of each other and thus diastereomers. We can also find this relation by comparing absolute configuration. Here on C2 they have the same configuration, while on C3 they have different. So they are diastereomers. Meso compounds. These are defined as achiral compounds with more than one chiral centers. Since they are achiral, so they are optically inactive despite having chiral centers. They have plane of symmetry. For example, Meso tartaric acid. In this molecule, we can see that there are two chiral centers and this is the plane of symmetry. This is the example with three chiral centers. This is the plane of symmetry. So this molecule is also a Meso compound. Cis 1,3-dimethyl cyclohexane. It has two chiral centers and a plane of symmetry. So this is a Meso compound. Let's have the example of 2,3-dibromobutane drawn in Newman projection. In this projection formula, it is hard to visualize plane of symmetry. In such situation, convert Newman projection to Fisher. Now we can see that there is a plane of symmetry. So this is also an example of Meso compound. That's all in this video. Please subscribe my channel and press the bell icon if you like this video. Thank you very much for watching this video.